Okay, excellent. I think we can start. Now we're gonna switch gears into the more technical aspects of the theory behind how to properly lattice a field theory. We are gonna start with the simplest cases, which are those of scalar fields in expanding backgrounds. Jorge Baeza Ballesteros is a PhD student in IFIC, senior PhD student, is gonna cover this topic. And well, we hope it's not very difficult as a starting point for getting really inside the lattice. But please let us know later on because, well, things are going to get later on more and more complicated as we introduce gauge fields. Remember, feel free to raise up your electronic hand during the lecture. Then I will let Jorge know that you have a question and we can do it on real time. The idea is now 1 hour and a half of lecture, such that after 45 minutes, we take 5 minutes break. I will let you know in that moment, Jorge, and then we do the second part afterwards. So I think the stage is yours, Jorge, please go ahead.
Okay, so thank you for the introduction, Danny. And I hope everybody is having a nice time and learning a lot during this school. So as Danny has said, in this lecture, I'm gonna cover how one formulates a scalar field theory in an expanding background in the lattice, and which are the different algorithms that we can use to solve that theory and to simulate the dynamics. In particular, this is what you have been, you have to see this as the theory behind the simulations you've been running in the previous practical session. And I'm also going to apply all the different things you viewed yesterday in both the sessions in the morning about different topics in cosmology, and then the session in the afternoon about algorithms. So this lecture will have two parts. We'll make a small break in between. First, I will cover the more theoretical part, in which I will explain how scalar fields in an expanding background can be put into the lattice, the different methods, the different approaches we can take. And then in the second part, I will explain how these methods, how the differential equations that we get can be solved using different numerical algorithms. And also I will try to highlight which are the advantages and the disadvantages of the different algorithms. So as Danny has said also, please feel free to raise your electronic hands and make any questions in the chat or anywhere if you have any question. So our starting point is gonna be a theory with a number of interacting real scalar fields, which have a canonically normalized kinetic term. So the starting point is just the action for the theory. We first consider a generic metric that we are now gonna to particularize to the Friedman-Lemaitre Robertson-Walker metric, the usual metric of an expanding background. Then we have the canonically normalized kinetic term for all the scalar fields appearing. I'm using this A label to label the different scalar fields in the theory. And then we consider a generic potential that can contain any kind of interaction between the different scalar fields. For example, in the previous session, in the practical session, we've been considering a theory that had two different scalar fields. One was the inflaton, the other one was the daughter field. And then the potential had two terms. One was the potential of the inflaton field, and then an interacting term between the potential and the inflaton and the daughter field. But in general, you can consider any kind of interaction and any number of scalar fields. And these same models, you can simulate them using CosmoLattice. You can consider in CosmoLattice as well any number of scalar fields and any type of potential. So what we do in order to put this theory in the lattice, first of all, is to rewrite it, to particularize the theory to an expanding background using this metric that was introduced yesterday. So it's the Friedman-Lemaitre Robertson-Walker metric, in which we consider a general alpha time. And then we rewrite the theory also using program variables. This was also introduced yesterday, and I think, and we also had a brief reminder in the previous session. So what we do is we use two different scales, one typically related to a typical field amplitude, that is this F star, and then omega star, that is related to a typical frequency of the model. And using these two scales, we rewrite all quantities in dimensionless variables. We rewrite all our equations in terms of dimensionless variables, so that we are able to put them in the computer. And I also want to remind that the choice of these scales has to be done wisely in order to keep all quantities that are going to appear in our theory to be order 1, because that's also more stable numerically. As you saw yesterday, there is this alpha time. Alpha is another parameter that you have to choose for your simulations. Alpha 0 is the usual cosmic time. Alpha equals to 1 is the conformal time usually used in cosmology. But you can use any value for alpha, and it's sometimes convenient to choose a fractionary value, such that the simulations are also more stable. So that this is something we can discuss later, and maybe you discuss it. So this is something you will discuss more in detail tomorrow in the practical session, when you see the model with a tangent and a generic power, in which the alpha can be chosen in a particular way to make the model run more smoothly The last comment I want to say is that I'm using this prime to refer to a generic time derivative with respect to this alpha time, this eta, which is the alpha time. So the action we get now here has three different terms. The first term is the kinetic term. The second term contains the gradients of the fields, and then the final term is the potential. So now we have our theory, which is given by this action in program variables, and we can obtain the equations of motion for each of the scalar fields by using the variational principle. So and this is some exercise that I suggest, that I think if you have some time, you should try to do. This is to get our action in the Friedmann-Lemaitre-Robertson-Walker background, and to consider a variation of the action, and applying the variational principle, try to get to this equation of motion. The main thing you have to take into account is that the A parameter is also a function of time. So we get this equation, which has different terms. This is the equation of motion for the scalar field, and it contains some different terms. The first one is the second derivative of the scalar field. Then we have the gradients of the field. This term, which is the Hubble friction, this third term, that contains the Hubble parameter, that is related to the Hubble parameter, and so it contains the effect of the expansion of the universe. And then the last term, which is as the potential term, is the usual force that runs, or that sources the expansion or the dynamics of the field. In addition to this equation of motion for the scalar field, the dynamics, since we are working in an expanding background, the dynamics have to be complemented by the equations of motion of the expanding background. And this equation of motion are the Friedmann equations. What you have to recall is that we are working in a model in which we have a scalar field that evolves in an expanding background, but this background is expanding due to the scalar field. So the equations of motions here, which are the Friedmann equations, are sourced by the energy densities associated to this scalar field. So we have two different equations, the Friedmann equations. The first Friedmann equation that we will consider separately, as I will mention in a moment. And then the second equation that is an actual that contains the second derivative of the scale factor, and we can regard it as a as an actual equation of motion for the scalar field. So rather than using both equations to solve for the dynamics of the scalar field, what we will do is to consider this second equation we will consider this second equation as the equation of motion, and we will solve this second Friedman equation together with the equation of motion for the scalar field, while the first Friedman equation will be used as a constraint to verify that we are conserving energy properly in our system. We are not conserving energy. Better to say that it will be as an equivalent of energy conservation in our expanding universe. So the only comment I want to make here before continuing is that MP here is the reduced Planck mass. And up to this point, does anyone have any question you want to ask? Okay, so then we have our equations that we want to solve, the equation for the scalar field and the equation for the scale factor. How do we solve them? We want to put them into a lattice. Which is the way in which we put them into a lattice? So the way we do them, since we are working with a very simple system that just contains scalar fields, is by using a simple prescription. We transform our continuum derivatives, our theory in the continuum, into a discrete theory. This is, we substitute our continuum derivatives for by lattice derivatives. And I want to make some comment here is that this is valid, this is enough to lattice an scalar theory, but this may not be enough, is usually not enough in the case in which you work with gauge fields, as you will see this afternoon and more in detail tomorrow when you cover non-abelian gauge fields. However, there are still two different choices, two different ways in which we can lattice our theory. The first one is to consider the equations of motion and apply this prescription directly into the equations of motion. So we get the equation of motion for the scalar field, and we substitute the derivatives, the time derivatives, and the spatial derivatives by discrete derivatives. The second option is to go a step backwards and to substitute directly the derivatives in the action to obtain a lattice version of the scalar field action. And then from that action, derive again, which are the equations of motion. So at this point, I would like to ask you or to have you thinking for a moment, which of these two options do you think is better? So if anyone has any guess or wants to try and guess. So Mohammed said has the things that the first one is better. So there is not a better option here. Both of them are valid. And for scalar fields, you can use either one. And indeed, we are going to use both of them depending on which algorithm we want to apply. It's better to start from one of them or from the other. However, when you work with gauge fields, when you later work with gauge fields, it's more convenient to use the second approach. And the reason is that when you work with the action, when you put the action into the lattice and then you derive the equation of motions, conservation laws appear automatically. And in particular, when you have gauge fields, this will mean that the equations that you derive from the lattice action will automatically obey the Gauss constraint. So you will get the Gauss constraint from, so they will directly obey the Gauss constraint. And indeed, for gauge fields, and in particular for non-abelian gauge fields, you need to go for the lattice actions because you have to wisely choose which are the dynamical variables, the degrees of freedom that you want to consider. So, but in any case, for our case, for the scalar fields, both options are valid. I'm just gonna work with the second one for now, but later on I will go back and consider again the first approach. So how do we, so let's consider this second approach in which we are gonna to discretize the action. And let's consider the action that we have derived before. And let's try to put it into a lattice. How do we do this? We do just two different, we have to choose a prescription, and the prescription I'm gonna choose is to use forward lattice derivatives as we saw yesterday. So these spatial derivatives, they are gonna be substituted by forward derivatives, which we are gonna consider that they live in the midpoints in between two lattice sites. In addition to put the action into the lattice, we have to change this integral by a sum, and note that the measure of the integral is being changed into this product here, where we have the lattice spacing and then the time steps that we are using. So after we do these changes, we get the following lattice action. Just a couple of things that should be commented here. The first thing is that when we multiply two different quantities in the lattice, like we have here in the first term or here in the second term, we need the different terms to live in the same points in the lattice. So the different quantities that we are multiplying need to live in the same points. So here we have the forward derivatives, which are defined as was shown yesterday. Here is the time derivative, and this one is the spatial derivative, and they live in the midpoints. So this lives, this means that this term here lives at semi-integer times, and this term here lives at integer times, but in between two spatial points. So how do we manage the boundary conditions? That's a very nice question. At this point, so the boundary conditions, what you should do is what where Paco explained yesterday. So Mohammed had asked, how do we manage the boundary conditions? And the way in which you manage boundary conditions is, so you consider some boundary conditions, and when you do this discretization, you just have to consider which boundary conditions you have decided to use. So for example, it could be the case that for the forward derivative for the point which is in the border, you need to consider, if you are using periodic boundary conditions for the field that lies in the last, so when you consider the derivative for a point that lies in the edge of the lattice, you may need to consider the difference between that point at the point that lies in the very beginning of the lattice. But in the end, that depends on how you choose the boundary conditions. Although there is no problem in defining this for different boundary conditions.
Yeah, but I mean, let's not complicate ourselves. I mean, the idea is typically we consider periodic boundary conditions.
Yeah, typically, the periodic.
And there is no problem whatsoever to impose them at the level of the action, you know, pretty much the same as what we were explaining yesterday.
Yeah. At this level, however, you don't need to worry about boundary conditions yet, because this is a discretization of the theory, but you can still have an infinite volume. Or if you have finite.
But okay, but it's a good pertinent question, because already you are thinking of a finite summation of lattice points there, no? So yeah, it's a pertinent question.
Okay. Yeah.
In the boundary, when you reach the boundary of your volume lattice in that summation, there you impose to the field amplitudes periodic boundary condition.
Yep.
It's that simple. Yeah.
Okay, so going back, we have the forward derivatives, and then the one thing you may have noticed is that this scale factor here has this subindex, and what this means is that as this forward time derivative lives at semi-integer times, we have to multiply it by the scale factor living also at semi-integer times. In the other terms, the spatial derivatives live at integer times, and so the scale factor by which we multiply it also live the scale factor by which we multiply it also lives at integer times. This means that overall the action has two different terms, some of which live at semi-integer times and other of which live at integer times, but this is not a problem per se. We can have the action having, as long as internally each of the terms is consistent, it's fine defining the action in this way, having different terms that live in different points in the lattice. In this case, and different points in time. So now we have our action, and what we want to do is to derive the equations of motion. How we do them? How we do that? In the usual way, we just consider a variation of this action with respect to time, and you can do that even if our action is in a discrete lattice. And this is something, also some exercise that I would recommend you to do. And you will find this equation of motion. So the first thing I want you to notice is that even if we were working with, even if the prescription we used to discretize the equations of motion was to substitute the derivatives by forward derivatives after applying the variational principle, we get backward derivatives in our equation of motion. And this is not in contradiction with what we did. This is just the result of applying the equation of motion, the applying the variational principle. And this also justifies some choices that, for instance, Adrian did yesterday afternoon, in which he wrote the Laplacian as the forward, as the consecutive application of a backward and a forward derivative, as this is what we get here for this Laplacian term. And then we also get the backward derivative here for the backward time derivative. And if now you see at which time do the different terms live, what you will observe is that this thing here inside of the brackets lives at semi-integer times, but then when we take the backward derivatives, we go from living at some time plus 1/2 to living at some integer time. And then the second term, the right-hand side of this equation also lives at integer times. And so the equation of motion we get from this action is indeed consistent with respect to the times in which the different terms live. So we have an equation of motion in which all the different terms are defined at integer times. And so it will be easier, it is suited to solve it using some numerical algorithm. So do you have any questions up to this point? So I see you have had a brief question in the chat, but it's solved. So the main message to get from this slide is that even if you're in a lattice, the same methods that we use in the continuum can be applied. In this case, the variational principle, and that we get an equation of motion that is suited to be solved using some numerical algorithms. So now we have our equation for the scalar field, but we still need an equation for the scale factor. Okay. Sorry. So we need an equation for the scale factor. And as I have said before, the equation of motion that we are going to use for the scale factor is the second Friedmann equation, as it is the one that contains the second derivative, the second time derivative of the scale factor. So this is the equation of motion that we are going to consider. And now we have to make a choice. At which time do we want our scale factor to live? Do we want to define the scale factor to live naturally then at integer times? Or do we want the scale factor to live at semi-integer times? And it turns out that this is just another prescription, another choice we can do. Any of the two choices is a valid option. So for example, we can choose the scale factor to be defined at semi-integer times, which would mean that we will define the time derivative of the scale factor we will be leaving at integer times. So we will define it in this way. The forward derivative of the scale factor defined at semi-integer times will be leaving at integer times. And then the second derivative of the scale factor, which is just the derivative of this b variable that we have just introduced, will be leaving at again at semi-integer times. This means that this equation here, we will rewrite it in this way. The main thing to notice is that as we have introduced before, there are these three energies that the expansion of the universe is sourced by the different energy the energy densities, the energy densities of the different energy components of the scalar fields. And there are different ones: the kinetic term, the gradient term, and the potential term. And the problem here is that the kinetic term is related to the time derivatives of the scalar field. And so let me go back to show this here. So these are the energy densities that we have, and the thing is that when we put them into the lattice, the kinetic energy is related to the average kinetic term, and so it's related to this time derivative of the scalar field. And so by default, it will live in semi-integer times. We are defining the time derivatives to live at semi-integer times. And so the kinetic terms, the kinetic energy is going to be defined at semi-integer times. On the other hand, the gradient term and the potential term, they are just functions of the field or of the spatial derivatives of the field. And since the field is defined at integer times, this means that the gradient and the potential energy densities will also be defined at integer times. So the kinetic energy density, semi-integer times, because the time derivative is defined at semi-integer times, the gradient and the potential terms, they live at integer times because the field and the spatial derivatives also live at integer times. Then when we go to solve or to write in the lattice the Friedman equation, and we choose the scale factor to live at semi-integer times, we need to write the gradient and the potential terms also at semi-integer times. And the way in which we do them is by averaging the values at some integer time and at the following time step. Is that well understood? However, there's also the other option. We can also do the opposite, meaning that we can also define the scale factor to live at integer times, and then its time derivative will be defined at semi-integer times, which is this b factor here that now lives at some time plus a half time step. And then the second time derivative, it will be sourced by the equation of motion, by the lattice version of this equation of motion. And now, since the scale factor lives at integer times, the second derivative will also live at integer times. And so we are fine with the gradient and the potential energy densities, but the kinetic energy density, we now need to define it as an average from the kinetic energy density half time step before the time in which we are interested, and a half time step after the time in which we are interested. So again, we define this kinetic energy density as an average. Is there a better option between these two prescriptions? No, both of them are fine. In CosmoLattice, we make an option, we choose one of them to solve the equation of motions, as we will see later, to use leapfrog, but everything is fine and you can use any of them. So let me make a brief summary of the things we've seen so far. We have discretized the scalar fields. So we have the way in which you have done that is by getting the action, considering the action of the scalar fields in an expanding background and discretizing the action, and from that action extracting the equation of motion, the equations of motion, and we got this equation here. And second, we have also discretized the equation of motion for the expanding universe. And in that case, we have obtained these two possibilities, depending on whether we decide that the scale factor lives at integer times, or it lives at semi-integer times, or it lives at integer times. And now the question is, how are we going to solve this equation of motion? And this is what I'm going to cover in the rest of this session, which are the numerical algorithms that one can apply to solve this equation of motion. But before going on, I would like to ask you again if you have any question or there's something you want me to comment more about. Otherwise, I know we have only been half an hour, but this may be the best moment to make a 5 minutes break, if you are fine with that, before going into the numerical part of the session.
You decide, Jorge, if you prefer to do the break here, that's absolutely fine, of course.
Yeah, so maybe let's do the break now.
Okay.
You can think about what we have covered and make any questions and we recombine in 5 minutes, maybe.
Very excellent. There's a question in the chat, Jorge. Do you want to read?
Oh, yeah. How are we accounting for the quantum nature of the fields? It seems to me like solving a classical field equation. So this is a nice question. We are solving classical field equations. Everything we are doing here is classical field equation. The way in which we are introducing this quantum nature of the fields is in the initial conditions. So the initial conditions are follow the expected form, the expected power spectrum from the primordial quantum fluctuations. But once after putting these equations in, we are solving the classical equation of motion of the field. We are solving the classical part of the field. And correct me, Danny, if I'm wrong, but the reason why we do this is because we are working at very high occupation numbers. And so we can approximate the behavior of the mean behavior of the field by the classical equation of motion.
Thank you. No, that's absolutely correct. This is a very nice question from Jaime. And certainly the answer of Jorge is perfect. Let me just add that, the whole point of doing these lattice simulations is based on the idea that certain physical scenarios always develop the semi-classical limit, meaning the large occupation number. If you wish, one way to see this is that you can think of the quantum nature of a field as encoded in the commutator, no? Think, for instance, of the commutator between pi and phi, no? Which in quantum mechanics and quantum field theory is 1 in natural units. Now, if the amplitude of your field fluctuations, both derivative and field amplitude in the corresponding units, natural units, reach 10 to 9, you see, the fact that I commute 10 to 9 with 10 to 9 plus 1, it's irrelevant. You see, that's precisely the point. So it turns out that there is a number of circumstances aka inflation, preheating, phase transition, cosmic defects, and other in between, where these circumstances are met. And that's when we can apply the lattice simulation. Yet, the initial condition, as Jorge was highlighting, typically comes from mimicking the distribution, the stochastic distribution as dictated by quantum mechanics, in particular, the power spectrum dictated by quantum mechanics. All right, so we don't do path integral, as for instance, lattice QCD, but we do the excitation of initial quantum fluctuations that become due to some instability mechanism. For instance, Paco introduced this yesterday, parametric resonance. That's a phenomenon that takes from vacuum initial fluctuations and drive them into exponentially large amplitudes. And he showed us a demonstration that in his practice. And that's when all of this becomes valid. You need some kind of instability or classical configuration from the beginning. Okay. So thanks for the question. Maybe I can add to that, that for instance, for the basic scenarios of a scalar field, like lambda phi to the fourth, running it in the long term with this kind of lattice techniques has been double checked against 2pi formalism that follows the correlators in the full quantum field theory approach, and the distributions are pretty much identical. All right, even when the system becomes pretty nonlinear. So essentially, this technique captures well, our lattice technique captures well the distribution of fields when there is this classicality notion in the dynamics. And the advantage of using the lattice is that then we can deal with the nonlinearities that otherwise you cannot. I'm gonna run to make a coffee actually downstairs. Okay, I'll be back in 2 minutes.
Okay, so we wait for you and then restart.
Thank you.
So maybe we can restart now. It's been a bit more than 5 minutes, but I think that's fine. Do you have any question of with what we have covered so far? Okay, so let me summarize a bit. We have written the scalar field equation in a version that is suited to be simulated in the lattice. And we have also done the same for the equation of motion of the scale factor, that is the second Friedman equation. And now I'm going to cover how to solve these equations. And I want you to try to go back to what Adrian covered yesterday and to try to remind yourself of the different methods he presented, because those are mainly the ones we are going to be using today. And the first thing I want you to notice is that you look at this equation here, at the equation for the scalar fields, for the scalar field, and what you see is that we have this term here inside, which is defined at semi-integer times, and then the full equation that is defined at integer times. And this should suggest you that this is already suited to do one of the methods that Adrian discussed very briefly yesterday, that is the leapfrog approach. So in the leapfrog approach, what we do is we have two different quantities that we want to evolve. One that is defined at integer times, another one that is defined at semi-integer times. And then we evolve one of them using the values of the other evaluated in the in-between times. And then we evolve the second one using the evolved value of the first, and we go one and the other alternatively and evolving the two quantities. In this case, for instance, what this figure seems to suggest is that the first quantity is a position, the second one is a velocity, but you can also do this the other way around. So in our case, the equation we were having for the scalar field suggests that we can do this. We can consider what was inside the brackets to be our quantity defined at semi-integer times, and we can consider what the full equation or the scalar field to be the quantity that is defined at integer times. However, there are still a different couple of things, different couple of ways in which you can think of choosing the different quantities and making the definitions, and they are all discussed in the art, and I'm going to make a brief comment about all of them here. The first option would be to use to define conjugate momentum, so we are going to evolve two quantities. The first one is going to be the scalar field that is defined at integer times. The second one is going to be a conjugate momentum, but there are different ways in which we can define this conjugate momentum. So the first way is by choosing this conjugate momentum to be defined just as the forward derivative, as the time derivative of the scalar field. And then we have to choose where the scale factor lives, and for this particular choice, it's convenient to choose the scale factor to live also at semi-integer times. The second option would be to do the same, but shifting what's defined at integer times at what is defined at semi-integer times. So in this second option, the scale factor will be would be defined at integer times, and also the conjugate momentum, and we would define the scalar field to live at integer times. This is a bit more complicated to see from the equation we saw yesterday, we saw before, but it's still a possibility you can use. And then the third and fourth options are just modifications of the two options above, but in which we define the conjugate momentum with this additional factor of the scale factor, so that the conjugate momentum is everything that was inside the brackets in the equation we had before. So all this here is the conjugate momentum. So let's see. So, and just a very brief, before going on, a very brief comment that Adrian also made yesterday, that is that the only limitation that leapfrog has is that you have two quantities, the momentum and the field, and they are always defined at different times. The field, or one of them, always lives at integer times, and the other always lives at semi-integer times. The problem is that when you want to measure, if you want to measure the energy, if you want to measure the field values, you usually want to measure everything at the same time. So when you want to do that, the solution is to do half a step with for one of the quantities, so that you define everything at the same time. You synchronize all the quantities, and then you make your measurements, and then you evolve that quantity by another half a step to put them again where you want it to be. For example, in this case, you will make first one half step, you will measure, and then you will do the second half step. Okay, let me. Okay, so now let me comment on all these possibilities. So the first option we were discussing about is the option this option in which we define the conjugate momentum just as the forward derivative of the scalar field, and we choose our scale factor to live at semi-integer times. The equation, the initial conditions that we need to solve the equations of motion are the scalar field and the time derivative of the scale factor defined at our initial time, and then the conjugate momentum and the scale factor itself defined not at the initial time, but half a step before the initial time, because we are going to evolve our equations doing these half steps. I want to make a comment here, and is that in CosmoLattice, what you have to do is to define everything at the initial time, because this half step is accounted for by doing initially only half a step rather than a full step for these quantities. So after doing this, what you first do, the first step is to solve for the scale factor and for the conjugate momentum. You do one full step for these quantities, and so you solve them at plus 1/2 and time step. So you have to solve these equations. The first one is just the equation of motion for the scale field, for the scale factor, which is pretty easy, and it allows you to define an average value for the scale factor at an integer time. And the second equation you have to solve is this equation for the conjugate momentum that has two terms. A first term that depends on the value of the conjugate momentum in the previous step, and then this second term that depends on the actual dynamics, on the actual grade Laplacian here, and the potential of the scalar fields. And the fact that this first term here contains this prefactor, that is a quotient before of the scale factor defined at the initial time and at the final time, means that if you try to rewrite your equation as the initial value of the scale factor plus some kernel times the time step you want to evolve, you will find that this kernel here depends not only on the scalar field and on the scale factor as you would like it to depend, but it also depends on the conjugate momentum itself. And this is a problem, since, as you saw yesterday, this means that the force is non-conservative, and then we should use a non-symplectic integrator, a more complicated algorithm to properly get this equation solved. So this means that if we were to use this leapfrog to solve the equation written in this particular manner, we will find this problem, and then the precision will be rather small. It will be only order the time step. So this suggests that using this prescription for the conjugate momentum is not the best option. The second possibility I showed you is more or less the same. You also made the definition of the conjugate momentum. We also made the definition of the conjugate momentum using the forward derivative, although now we shifted whether things were defined at integer or semi-integer times. But the conclusion we get is the same. When we write down the equation for the evolution equation for the scale factor, the step we are going to do to evolve the scale factor, the conjugate momentum, we find that the kernel also depends on the conjugate momentum, and so the force is non-conservative. So we also want to avoid this. What we do instead, the best option is to define the conjugate momentum having this prefactor here, having this power of the scale factor. And then what we will do is just to solve for the conjugate momentum using this simpler equation. So since we have defined the conjugate momentum to be everything that was inside the brackets before, we can just we can just explicitly write the forward derivatives and separate this quantity here. And I see that this is missing the time step. So we can evolve the conjugate momentum and find that the kernel we have now does not depend on the momentum itself. It now only depends on it now only depends on the field and on the scale factor. And so it means that the force we are solving now, the system we are solving now, has a conservative force. And so we can solve it using this staggered leapfrog properly and get a precision which is of the order of the time step squared. So to solve these things, we started with the initial conditions. We solved for the conjugate momentum. We solve for the derivative of the scale factor, which is given by these quantities here, where note that we have to do an average for the kinetic term. And then so this is the first part of the evolution, the first of the steps in the leapfrog. The second one is evolving the scale factor and the scalar field. And as before, the only comment I want to say is that in this prescription, we are considering the scale factor to live at integer times. And so the semi-integer time, the scale factor at semi-integer times, such as this value here, or this one entering here, you have to compute it doing an average between the initial value and the value after evolving one time step. And finally, after computing all these quantities, we use them again as the initial conditions for the following iteration. So we evolve them. We evolve the conjugate momentum, the scale factor, the scalar field, and then we start again using the results from the previous iteration for the following one, as is usual for these numerical methods. The final comment is that here after doing the full iteration, we can also measure the Hubble constraint. And this is the way in which we define the Hubble constraint. We can measure it at semi-integer times directly to check for equivalent to energy conservation. And this is indeed the method. This third option for the staggered leapfrog is the one that is available in CosmoLattice. This is the way in which the scalar fields are evolved in CosmoLattice if you choose leapfrog as your preferred evolution algorithm. There was also a fourth option. It's discussed in the art. It's mostly similar to the one we have just discussed, so I'm not going to cover it in detail. But if you have any question about it, or if you go to the art and look for this option, it's pretty much the same. So this is the leapfrog. Let me know if you have any question about this. Otherwise, I will move on to a variation or a more so I know, yes, so yesterday Adrian introduced the Verlet algorithms first, and then put the leapfrog as a particular case. Historically, it was the opposite. The leapfrog was the first developed, and then the Verlet were developed like a century later. And the way in which the Verlet algorithms work is by changing. So effectively, what they do is that they change the evolution of the things that were defined at semi-integer time steps into two sub-steps, so that indeed what you do is you have two quantities that you want to evolve from an integer time to another integer time, and everything is now defined at integer times. And the way in which you do this is you evolve one of the quantities by half time step. You use the results at the semi-integer time to evolve for a full step the other quantity, and then you evolve by half time step again the first quantity. So after the iteration, everything is again defined at integer time steps. So in this case, in order to formulate the equations for the scalar field in a way that is suitable to apply the Verlet algorithms, it's more convenient to go back to the continuum, and instead of using this approach in which we discretize the action for the model, we discretize the equation of motion. So let me review or summarize again which are the equations of motion. In the continuum, we had, this was the equation of motion for the scalar field, but rather than directly discretizing this and trying to solve this, it's more convenient to note that these first two terms just come from applying the time derivative to another term. And so it's possible to rewrite the equation of motion for the scalar field in this way. So we are we are putting together the time derivative of the scalar field and the scale factor in this way. So the second derivative and the Hubble term and the friction term, they are getting together into this single term. And you should see this as a very similar equation to the equation we had before for after applying the lattice action approach. So what we are going to do is kind of the same. We are going to define a conjugate momentum that is the quantity inside this time derivative. And then we are going to use this to rewrite our second order differential equation as a first order differential equation. So you can also think that this could have been done before for the previous approach, and you would be completely right. The thing I showed you before was just how to do this, how to do that from the action, and now I'm doing it from the equations of motion. So after defining this conjugate momentum, we can write the equation, this second order differential equation, into a system of two first order differential equations. First, we have the first one that is just this definition here. So the derivative of the scalar field is just related to the conjugate momentum. And this equation is what we call the drift. And then the second one is that the derivative of the conjugate momentum is this term here, is just related to the gradients and the potential of the scalar field. And this is the kernel that we were introducing before, and it's also known as the kick. So what are these Verlet algorithms? These Verlet algorithms are just a way of solving this drift and this kick in an iterative manner. So in the same way in which we write the scalar field as this system of equation, we also saw that the equations for the scale factor can also be rewritten in this same way. Note now that contrary to what we did before, we are still in the continuum, and so we don't have to worry on whether things live at integer or semi-integer times. We are in the continuum. So we have the equations we want to discretize, we have the equations we want to solve, and we are now gonna discretize them using this approach in which we directly discretize the equation of motion. And this is what is done in the Verlet's algorithms, and it can be done in two different manners. We can either, as I have said before, the Verlet algorithms work by solving half time step one quantity, then a full time step the other quantity, and finally half time step the first quantity. And they come in two different flavors: the velocity Verlet algorithms and the position Verlet algorithms. And while they are both very similar, I'm going to cover a bit more in detail the velocity Verlet algorithms. And these velocity Verlet algorithms, each step of the iteration consists on solving half time step the kick, then solving the drift, and then solving the kick again for a half time step. And by doing this, what you can achieve is a precision of order the time step square. So let me explain how they work. We start with some initial conditions defined, which are just the value of the field, its conjugate momentum, the scale factor, and the derivative of the scale factor defined at the initial time. We solve the kick for half time step. This is, we evolve the derivatives. We evolve the derivative of the scale factor, and we evolve the derivative of the conjugate momentum. And these are the equations we have to solve. So the derivative is just the quantity we want to evolve, or the initial quantity we had, plus the kernel, the corresponding kernels. And then we obtain the values of these quantities at half time step in the forward. Then we use these results to solve the drift. This is to evolve the scale factor and the scalar field. And in this case, we do a full step, so we get the results for a full step later. And finally, we use these evolved results to again evolve the conjugate momentum and the derivative of the scale factor and obtain them at the final time in which we want to get the results. Okay, so we do half a step, then a full step of the other quantities, and then half a step of the first quantities. And this is something you did yesterday with Adrian, and I think there was an example and an implementation of this for a very simple model in one of the Julia notebooks he shared. So this was velocity Verlet. You can also do the opposite. You can also do the position Verlet algorithms, which are done in the opposite way. You do half a step of the drift so you evolve the scale factor and the scalar field for half time step. You do a full step of the kick, a full step in which you evolve the conjugate momentum and the derivative of the scale factor, and finally a final half step of the scalar field and the scale factor. So they are both very similar, and I would like you to think a bit about them, ask me any questions about them if you have, and try to answer the question of which one of them you think is faster. So in this particular case, which one of these two flavors of the Verlet algorithm do you think is faster for solving scalar fields in an expanding universe? So
yeah, but
yeah. So
sorry,
Alfredo,
second, but why?
no, so Alfredo is right. Kick looks more difficult. Kick is more difficult, and in particular, evaluating all these energy densities is very expensive because you have to average over all the lattice. So doing it once rather than twice is slightly faster. So when you are working with this self-consistent expansion, when you are trying to evolve the universe at the same source by the matter fields that you have in your theory, then the position variability is slightly faster. It's not like an extremely big improvement, but it's faster. So very nice answer. So let me now move into a bit or more. So these velocity variable algorithms have the same precision as the leapfrog algorithms we were mentioning before. But there are other algorithms that were also discussed yesterday by Adrian, which lead to a better accuracy. In particular, one of those algorithms are the Runge-Kutta algorithms, which are probably the best known numerical algorithms for solving differential equations. And they are usually based on making different predictions for the result and using those predictions to make better predictions. And in this case, they are more generic because they can also be used to solve non-symplectic systems. So you can consider some model in which the kernel for the scalar fields depends on the scale factors. The kernel for the conjugate momentum depends on the conjugate momentum itself. So for example, here you can consider some kernel that has some factor proportional to the conjugate momentum. And these Runge-Kutta algorithms allow you to solve. And again, there are a myriad, there are plenty of Runge-Kutta algorithms of different versions of implementing them. There are, you can have different orders of precision. You can have algorithms that go to order time step squared, to order time step to the fourth, to order time step to the sixth, etc. And you have also explicit and implicit algorithms, depending on whether the time steps, the internal time steps they do are constant, are fixed, or they are adaptive. And there are also other types of Runge-Kutta algorithms which reuse the prediction variables. So they are the so-called low storage Runge-Kutta algorithms. And I think they will be discussed they may be discussed by Ben and Toby, or Ben or Toby on Friday. And one of those cases will be published because these Runge-Kutta algorithms are not yet available in the public branch of CosmoLattice, but we will make one of these low storage versions of the Runge-Kutta algorithms available in the early future. So let me briefly show you a couple examples of these Runge-Kutta algorithms. This is the order 2 algorithm. It has the same precision as the leapfrog and the velocity and the Verlet algorithms, but the way in which it works is that you start with some initial conditions, and then you compute some prediction, which is the p = 1, and you use this first prediction to compute the second prediction, the p = 2, and then you combine both of them to get the final result. The same happens in the case in which you go to Runge-Kutta 4, which I think is the most widely known algorithm for solving differential equations. And in this case, you compute 4 different predictions, and then you get the final result by combining all 4 of them. And this is much more accurate than the typical Verlet and the typical leapfrog algorithms, but it comes with a drawback, with some cost. The first cost is that you have to compute more quantities, so each step is a bit more expensive. The second drawback is that you need to store these quantities in memory, and when you are running very big simulations, this can be a problem, because you are not just evolving your fields. For each field you are evolving, you need to store 3 or 4 intermediate quantities. And that's why I was mentioning that there are some variations of these methods. They call low storage Runge-Kutta, in which the things are done in a manner that rather than saving 4 intermediate quantities, it's enough to save one of them. But the advantage is that they allow you to reach these higher precisions, and more than that, they also allow you to solve these non-symplectic systems. So if you want to go to one of these systems, you need to use Runge-Kutta. And in particular, one of these system arises when you consider non-minimally coupled scalar fields to the curvature tensor, to the curvature scalar, to the scalar curvature. And this is what's going to be discussed on Friday by Ben. No, by Toby.
Sorry, actually, it's going to be on Thursday at the end.
It's on Thursday?
And yeah, and Ben is not going to be able to make it. It's going to be Nico taking over. So it's going to be Toby and Nico. Sorry.
Okay, so it's going to be Toby and Nico on Thursday. Sorry for the
no worries, sorry.
scheduling. It was on the last day last year. So it's on Thursday this year. Yeah. So yeah. Finally, the last couple, if you have any question about these things, these Runge-Kutta methods, just ask them now, or maybe later. But if you have any question now, you can ask them. Otherwise, I'm gonna move to the last type of numerical methods that we want to discuss, which are these the so-called Yoshida methods after their creator, Yoshida.
Jorge, just one comment before you jump into Yoshida integrators. Yeah, just to remind everybody that the explicit form of these algorithms that Jorge is showing here are all written down in full detail with derivation and the full details and so on in the review. Okay, remember there's the review and there's the manual. In the review document from 2020, we have all these formulas derived and written down in full detail.
Yep. And also apply to more complicated systems like with gauge fields and everything.
That's right.
Yeah. Yeah. So the last methods I'm gonna discuss are these higher order symplectic integrators, which are known as the Yoshida methods, and they are just a generalization of the Verlet algorithms we were discussing before. So in this case, we are going back to the symplectic system. So we are going back to systems in which the kernel for the conjugate momentum does not depend on itself. It only depends on the scale factor and the scalar fields. So contrary to what we having before, the kernel does not have any term depending on the conjugate momentum. And the way in which we are going to solve them is by applying velocity Verlet in a very wise manner. What does it mean? What it means is that we have our initial conditions defined at some time, eta 0, eta naught, and we want to solve to obtain the result after some time. So we want to apply a time step evolution of this algorithm and obtain the result at some eta 1. So if we were doing velocity Verlet, it would be pretty simple. We will just do half an evolution of one of the quantities. Then we will evolve the other quantity by full time step. And then we will go back and evolve the first quantity by another half step, time step. And in this way, we will achieve an order delta t squared precision, which is fine in some cases, but if you in some other cases you may want to go to a very big precision, and just reducing the time step is not efficient. The efficient way is to improve your algorithm. So the idea of these Yoshida methods is to split the step you want to do into smaller time steps. So these delta eta p's, such that you apply the velocity Verlet in each of these algorithms separate. So what you will do is, for the first sub time step, you will apply the kick, then you will do the drift, and then you will do the kick again. So Danny, can you confirm me that you are seeing the colors?
We see the colors what you are
Okay.
doing, yes.
Perfect. I was just worried. So you will do these smaller steps of velocity variable, and you will repeat this for all these sub intervals of your total iteration. So you start with these initial conditions, and then for each of these iterations, you solve the kick, the drift, the kick, and the drift, or the drift, the kick, drift, kick, as we were mentioning before. And what you end is, after doing this for all the steps, you will end with some results at the final time. So what's the point of doing this? Because this, at the first glance, this may seem to you like we are just making our time step smaller. The idea is that we are not making the time step smaller, but rather we are choosing the time steps to be different. So we are dividing one full time step into a smaller time steps, which have a different size, such that these sizes are chosen to cancel errors to some order. So in particular, if you were to use, for instance, 3 time steps, you will be achieving a precision of order delta t to the 4. And a very interesting thing is that these quantities here, so these numbers are numbers that add up to 1 because we are doing a full time step, but also that may be negative in some cases. For example, in the order delta t to the 4, which is the one I was mentioning, you have the first time step that goes forward in time, then the second that goes backward, and then a third time step that goes forward again. So in the end, you end in the time in which the time you wanted, and you have achieved a better precision. Are these methods more expensive than doing a velocity variable, for instance? They are, because you have to do more time steps, but they also achieve a better precision. And at some point, it's, as I was saying, it's not worth going to a smaller time steps. It's preferable to go for a better algorithm. And in CosmoLattice, indeed, you have available all methods up to order 10. And here I have this is a table from the art, in which you have summarized the different numerical values. And it turns out that there is no reason to go farther than order 10, because with order 10, you achieve machine precision with double numbers for most of the applications, I would say. I mean, you still have to choose wisely the time step, but for a reasonable time step, you go into order 10, you have machine precision. So a brief summary, these methods are a generalization of velocity variable or the variable algorithms. You can also generalize the position variable, in which can only be applied to symplectic problems, to problems in which the kernel for the conjugate momenta does not depend on the conjugate momenta itself, but they allow you, by wisely choosing some intermediate steps, to obtain very large precision, or very large precision. And this was the last method I was going to cover. So if you have any question, you can ask it.
Thank you. So Jorge, you finished the lecture?
Yeah, so a brief summary. So in this lecture, I have covered how one can lattice-ize, so how one can put in the lattice a theory for a scalar field in an expanding background, and which are the different which are some of the numerical algorithms that one can use to solve the equations of motion that we obtain. So we have seen that there were two methods of formulating the scalar field theory in the expanding background in the lattice: the equation of motion approach, in which we discretize the equation of motion, and the lattice action approach, in which we discretize the action and then derive some discrete equations of motion. And we have seen also that each of them has some advantages and some disadvantages, and they are in some sense complementary. They complement each other. And we have also covered different numerical algorithms, from the very simple leapfrog to the position and velocity Verlet, and the more complicated Runge-Kutta, which is valid for non-symplectic models, and then the Yoshida methods, which are a generalization of the Verlet algorithms. So thank you for your attention, and feel free to ask any question.
Thank you very much, Jorge, for the nice lecture and sticking to time. Okay, we are officially now in the lunch break, but we definitely have 5 or 10 minutes if somebody wants to ask some questions to Jorge. As you see, now it got a bit more technical.
Yeah.
It requires you to study a little bit, and this is why we were referring to the review. Jorge referred to it as the art. Okay, the art is because
a couple times.
all the art of simulating the early universe. So normally we refer to it to the art. Isaac, please, you can unmute yourself and go ahead.
Yeah.
Yeah, hi. No, I was just going to ask you briefly, what's the reason you have actually implemented so many different basically integration schemes? Like, because I would assume that, well.
So I think this is something that I was not involved in the implementation, but they are mostly, so the implementation of these Yoshida methods is for free. Once you have the Verlet, it's just a matter of saying, okay, make sub-steps with this size, and it's pretty straightforward. The Runge-Kutta is not implemented.
Oh, that's actually not implemented, I see.
So it is implemented.
It's implemented, but it's not implemented in the public version, and it's just one version of the Runge-Kutta implemented.
Which one, RK4?
Yeah, so I think it's RK3 low storage, which is a variation, because I think it's...
We have different versions depending on the scenario, you know. For action inflation, we have RK2. For a scalar field, we have RK2, 3, and 4 different flavors.
Oh. No, but so basically, depending on the physics scenarios, have you concluded that some of these integration schemes work better than others, or?
So the thing is, it's clear that when you have a non-conservative system, okay, that in your kernels you have conjugate momentum, you are forced immediately to go to Runge-Kutta. You know, alternatively, you could do what is called implicit. I think it's called Gauss legend.
Yeah, so the Gauss legend is also covered in the review.
Yeah,
okay.
But the thing is, at the end of the day, there are not really so many algorithms as it looks, because, you know, there is, on the one hand, to second order, there is Verlet integration and leapfrog, and in reality, they are the same. Okay, they are really the same. It's just how you look at them. Okay. The advantage of Verlet is that it allows for the generalization of Yoshida, which then is higher order. Okay, and that's how
I see. Okay.
You know, and then the advantage of Runge-Kutta is that it allows for non-conservative forces. So majority of standard canonical theories, scalar gauge theories, standard thing, you can write the kernels in conservative manner, and then you can use the Verlet integration or leapfrog. You know, however, in very interesting cases that Jorge brought up, like for instance, non-minimal gravitational interactions, or in axial interactions, we are rather forced to go to Runge-Kutta, and we will release those algorithms in due time, which is hopefully for sure next year.
Okay.
Yeah, there are other numerical algorithms. If you go to other applications, there are also algorithms in which you evolve each of the fields with different time steps, which may be suited to other two other physical problems that we have not faced, I think, Danny.
We do have implemented the one of the Runge-Kutta flavors comes with time-dependent time step. This can be convenient for accuracy reasons.
Yeah, but you use the same time step for all the fields.
So in these cases, do you choose the time steps to comply with the CFO condition, or how do you determine the
energy conservation? Typically, that's the so that's the problem, that at every time step you have to check how good is your energy conservation, and if it's not good enough, you have to decrease your time step. And it can be done on real time, but then it becomes very slowly running, you know. On the other hand, it can be the way to solve a situation in which you would crash otherwise your dynamics.
Yeah. Okay, thank you.
At the end of the day, let me just emphasize this. You should picture CosmoLattice as a platform where we collect all kind of interactions, so all kind of dynamics and algorithms to solve them. But you may have your own type of dynamics you want to solve, for instance, fluid dynamics, you know, and you may have to implement your own algorithm, you know. So what you should really see, CosmoLattice is the platform that provides a language in order to do that. It's a platform. Okay.
I see.
Devika, please go ahead.
Hi, yeah. So my question is for the Runge-Kutta algorithm, you mentioned that one of the issues is you have to store a larger number of quantities, but is that not also a problem for the higher order velocity Verlet algorithms because you have so many steps?
No, because in the velocity Verlet, in this higher order velocity Verlet, you are evolving. So you have many steps, but you use the same, so you have the initial field and you evolve the initial field for each of the steps. So you are always using the same memory. So this higher order velocity Verlets have to be seen as doing velocity Verlet, but in sub-steps. So there is no requirement of additional memory. So you just, each step supersedes the previous one.
Oh, okay. So you're basically just adding it to the same quantity at each step. Okay, I understand. Thank you.
Excellent questions. Okay, guys, do you have more questions? If not, remember in any case that after the lecture, the last lecture of the day, we are happy to speak for another half an hour in case you have questions of running CosmoLattice, installing it, etc., or the theory itself. Okay. Okay. Final chance. Is there any question maybe addressed to Jorge at this point?
Yeah, and if you have any question later during the week, feel free to write me in Slack or any other method you find comfortable for writing me. Like you can also send me an email.
Yeah, Slack would be very appropriate. Thanks for bringing up that, Jorge, because then it remains there, visible to everybody, and you know if the question is of global interest, then
if you make the question in public, it's for everybody. You can also make the question, as Danny has pointed out, although you can also make the question in a private, in a direct message to me. Better, maybe if you find that it could be interesting, just raise the question on the public chat. But don't feel forced to do so. You can also ask the question via direct message.
Okay, I think if there are no more questions here, let me stop recording.